class, I'd like to finish talking about some of the topics that came up today during our discussion. So the first one, we had already come up with the Taylor polynomial and started talking about the remainder. The Lagrange error bound will be f raised to the n plus 1 with some value of x plugged in times x minus c raised to the n plus 1 over n plus 1 factorial. So the next term was some value of x in between 0 and your c value. Now when I presented this to you in class, I said that we will use the c value that's given in the problem. Okay? So, because that would usually be the maximum. What I want you to think about there is that value will just be the maximum that it could be, therefore giving you the largest error bound. So, this will be the largest possible error. This term right here, the r sub n, is all of the Taylor series terms added together. And that'll give you your largest possible remainder. So applying that to the problem that we worked in class, we found out that P sub 1 was 0.099833333. We used our calculator to plug in sine of 0.1 to see how close our approximation was. Well, if you take the difference, that is the true error. So this value right here, 0.00000008335, is the actual error. That's pretty good error. I wish all errors were that good. The error bound is what you will be asked to find. So that means we're going to take the fourth derivative of sine x, which happens to be sine x, plug in that funny x value that's somewhere between 0 and 1 times x to the fourth over 4 factorial. The maximum value that any sine value is going to be is 1. So that is what I am going to use for that value. So I'm really going to say 1 times 0.1 to the 4th over 4 factorial. 0.1, remember, is what I was approximating. So that gives me the 0.000004 as my error bound. So this term right here, x minus x cubed over 3 factorial, is what we used to approximate our third degree Taylor polynomial, gave us 0.099833. We know that's less than sine of 0.1 because we actually plugged that in our calculator, and that value will be less than our error bound. So 0.09833 is what I already calculated plus 0.00004. So our error bound is the 0.000004, and that our actual error is less than that. Okay, so that is our error bound. Another problem that we talked about in class today was, does this series converge absolutely or conditionally? It was one of your homework problems. And we knew by the alternating series test that the alternating series converges. The question came up, does it converge conditionally or absolutely? So we need to know about the summation of 1 over n times natural log of n. Does it converge? So we talked about comparing it to 1 over n, the harmonic series, and decided that because we can compare it to 1 over n, that it does diverge. We weren't so sure on that, so let's apply a different test. Let's look at the integral test. So the integral from 1 to infinity of 1 over x natural log of x dx, we need to take the limit integral here. And we can see that by the integral test, that yes, I have indeed proved that I will get infinity, so it diverges. So that means our original problem, the summation of -1 to the n, or alternating series, does converge conditionally. Remember that natural log of n does not count as a power. Just like sine of n or cosine of n does not count as a power. So this is just to degree 1 in the denominator. Okay? I hope that helps. I'll see you in class tomorrow.